Next, we want to consider taking integrals of arithmetic combinations of certain types of functions. So by this, I mean maybe what happens if we take a common function and we multiply it by 5, or what happens if we take two common functions and we add them together. So we'll start with a couple examples, and then we'll state a couple of general rules. So if we want to compute the integral of -2 cosine of x dx, we're going to think about the fact that if I want to find a function whose derivative is -2 cos x dx, well, I know I'd better start off with some kind of sine function. The derivative of sine is cosine, after all. So the way that I modify this function in order to account for the -2 out front of the cosine is I put a -2 out front of the sine. And this is because of our constant multiple rule for derivatives, which says when you have a function and you multiply it by a constant, the constant sticks around when taking the derivative. In other words, if I were to take the derivative of -2 sine x, I would get -2 times the derivative of sine x. And the derivative of sine of x I know to be cosine, so this is -2 cos x, which is what we want. So we have -2 sine x plus c here for the integral of -2 cosine of x. In other words, it certainly seems like just like our derivative rule, our derivative constant multiple rule, which says constant multiples stick around, the integral constant multiple rule should be the same. Constant multiples are going to stick around when we're taking their integrals. Next up, we want to think about, well, what's the integral of 1 over x plus e to the x? And one thing that we know about derivatives is that the derivative of a sum is the sum of derivatives. Meaning that here, if I want to reverse that process, so if I want to talk about whose function or whose derivative is 1 over x plus e to the x, well, I'd better think about the antiderivatives of the individual pieces. So the antiderivative of 1 over x we know to be natural log of the absolute value of x. The antiderivative of e to the x we know to be e to the x again. And if I want to come up with a combination of these functions whose derivative is 1 over x plus e to the x, it's probably pretty reasonable to add them, and then add c. And this is because if I were to use the corresponding derivative rule, d dx of natural log of the absolute value of x plus e to the x plus any constant, the derivative applies to each piece of the sum. So this is d dx of natural log of absolute value of x plus d dx of e to the x plus d dx of the constant. And the derivative of natural log of x is my 1 over x. Derivative of e to the x is e to the x. And the derivative of the constant is 0. So I find that the derivative of this function, natural log of absolute value x plus e to the x plus c, is the integrand that I'm looking for, that 1 over x plus e to the x. So it seems that because integrals preserve constant multiples, because derivatives preserve constant multiples, and because derivatives preserve sums, we have the same thing as true of integrals. Integrals are going to preserve constant multiples, integrals are going to preserve sums. And in fact, that is exactly what we'll find with some of these derivative rules here, or some of these integral rules here. So we have a sum rule for integrals, which says that the integral of f plus g is the integral of f plus the integral of g. We have a constant multiple rule as well, which says that the integral of a constant multiple is the constant times the integral. And we had a couple other rules for derivatives, like the chain rule, the product rule, and the quotient rule. And we can state those in terms of derivatives, but for the moment, we don't really know how to take what the corresponding integral rules are. So let's go ahead and get a little bit of practice using our sum and constant multiple rules, namely with a couple of these different types of functions here. So we have an integral now of -2x cubed plus 7x to the 4 plus e to the pi dx. So the first thing that we want to identify is that we have a lot of addition going on here. So let's use our sum rule first. This is going to be equal to the integral of -2x cubed dx plus the integral of 7x to the 4 dx plus the integral of e to the pi dx. So we're getting a little bit better here in the sense that I maybe don't know a rule for taking the integral of minus 2x cubed, but I do know how to take the integral of x cubed. So we're going to apply my constant multiple rule right now and factor that minus 2 out front of the integral. So this is minus 2 integral of x cubed dx plus 7 times the integral of x to the 4 dx plus, well, there's no, well, I guess we could call this the constant multiple of e to the x, or e to the pi. Remember that e to the pi is just a number, and we could factor that out front of the integral. So this is the integral of dx. And now I can apply my power rules to each of these different pieces here. So this is minus 2 times x cubed over 3. We still need a constant, so maybe let's call it c1. The integral of x to the 4 is going to be x to the 5 over 5. And the integral of 1, well, we know that a function whose derivative, we need a plus another constant, maybe we'll call that c2. And let's see, we have e to the pi still, and the integral of 1 is x plus c3. Cool. So with all of this, notice that we've kind of written down a c for every term. If we call c1 plus c2 plus c3, we can simplify our writing a little bit and write this as minus 2x cubed over 3 plus 7x to the 5th over 5 plus e to the pi times x plus c. So even though we've added up a lot of terms here, and even though maybe we wrote down a different constant every time we computed an integral, in the end, we can always just call each of these constants, we can add them all up and give them a new name called c, and that means that we only have to write down one constant of integration here rather than writing down one for each term. So in general, whenever we're doing an antiderivative, we're just going to write down one constant. All right, so that was example 13. Now for example 14, we want to take a look here at minus 2 over root 1 minus x squared plus 1 over 4 plus 4x squared dx. So these terms look similar to some terms that we've seen earlier. Having this 1 minus x squared and a square root in the denominator looks a lot like the derivative of arcsine. Having this 4 plus 4x squared in a denominator here looks kind of like the derivative of arctangent, but we're going to need to do a little bit of manipulation first before we can actually compute those things. So here, maybe first what I want to do is use my sum rule and break this up into two pieces. So this is the integral of minus 2 over square root 1 minus x squared dx plus the integral of 1 over 4 plus 4x squared dx. Here in this first term, this minus 2 in my numerator, well, I'd like it if it were a 1, because I know what to do if there's a 1 in the numerator. So maybe I'll just factor that minus 2 out front of the integral. Minus 2 times the integral of 1 over root 1 minus x squared dx. So I'm applying my constant multiple rule there. For this second integral, I would like it a lot if instead of 4 plus 4x squared, that were 1 plus 1x squared. So maybe I'll factor a 1/4 out of that integral. So this is 1/4 times 1 over 1 plus x squared dx. Continuing on, well, I now know that I have from my table that the integral of 1 over root 1 minus x squared is arcsine of x. The integral here, well, 1 over 1 plus x squared, that has integral arctangent. And this 1 over 4, we should maybe factor out front of the integral first. So this is 1 over 4 integral of 1 over 1 plus x squared dx. And now we can use the fact that the integral of 1 over 1 plus x squared is arctangent. And we have our plus c at the end. So hopefully this has given us a little bit of practice with some of these initial integral rules, and you'll have more practice on homework in order to solidify your understanding of how to use these rules.